Hello, excited to be here for another movement learning live stream where the material that I'm currently working with, reviewing from the perspective of being a somatic educator, are the Feynman lectures. Um, and although last week I didn't do a very good job getting through the chapter on vectors, got very bogged down in some, I guess, geometry. Um, uh, and I haven't exactly caught up. I'm gonna move forward uh, and um, continue with characteristics of force today. Um, so if you want to continue along, uh, you can find this material fairly easily online. Feynman lectures hosted at Caltech. And as always, I intend to start around 10 o'clock. So if somehow you're catching this and you were expecting me a half hour ago, then I'm sorry. I'm trying to do better. But a big part of this is not just going through the material, but trying to attend to myself as I do it. And I think respecting time slots with you, like you're a client, is appropriate. And I'm going to try to do better. Um, but I am trying to also attend to myself as I do it. And yeah, I'm having actually a little bit of discomfort today. Um, so maybe if you're wherever you're watching this, if you are, you can chime. I should have a ticker, like guess which part of Ryan's in spasm today. Like could be a little ticker going across the bottom. Um, but rather than getting myself all right before doing this, I'm going to try to negotiate, paying attention to myself as I think about this material, and maybe some of my kinks will unkink over the next little bit. In a situation where I think most people would expect my situation to just get worse over time because I'm doing quote unquote desk work, or people could look at aspects of my so called ergonomics and decide that something is suboptimal and therefore that I should be experiencing a kind of diminution in comfort over time. But my actual experience is often that when I can attend to myself, even if it's in a more compromising situation, like being in a chair, um, that that being able to apply Feldenkrais method lets me actually get more comfortable over time. So I'll give you a concrete example. Was like my original chronic pain problem was a sciatic pain when I was around 12 years old. And if I was sitting in a chair for a long time, only about 40 minutes, I guess was a long time, sitting in a chair for about 40 minutes, the pain would get quite bad. Um, and Sorry, distracted by my cell phone. And after I was about halfway through my Feldenkrais practitioner training, I went on an airplane flight, about 3 hours with a couple awareness through movement recordings on my phone with me, and um, and actually did Feldenkrais methods in visualization space on the plane. So I was imagining that I was in whatever position the lesson was being described as, and I was imagining doing the movements. And um, that's not an easy thing. Like it wasn't an ability that I originally had to actually visualize movement that way. It took some practice to build up that capacity. But then once I had it, um, After that flight, I get up and I feel much better than when I sat down. It was as if I had been doing all that actual movement or quote unquote exercise over those 3 hours. I was feeling a lot of the benefits from having been improving my self organization through voluntary movement play. I was still doing it, even though I wasn't actually explicitly doing large movements. It was proving for myself that the process worked. And ever since I experienced that for myself, it was very empowering because, yeah, I can improve my organization in all kinds of situations. I hope you're comfortable, whatever your situation is. It's difficult to be comfortable these days. If one focuses on their own comfort and they actually feel it, then in some part, it's a level of dissociation from the discomfort that's integrated into all the other interactions in the world. In other words, being aware of your discomfort is okay because there's plenty of things to be uncomfortable about. Being aware of these things is not a not a shortcut. So getting this material in front, maybe this will be a lot more comfortable for me. Does that say dry forces are complicated? I'll be distracted by my phone a little bit. There's a nice conversation with organizers that I collaborate with. They're important. Maybe I'll bring some of that conversation more directly into the picture here. Oh, sorry. I keep bumping into my microphone. I need to stop doing that. So yeah, you should be able to find me on a couple platforms right now. Alright, I guess I'll scroll down this at least to get started. Does that say driving force? What is that? What is it even saying there? What is a force? Yeah, you're watching me do a lot of random social things, but these are must be integrated. These relationships matter. Hmm. And you can see the material for yourself. Maybe if you have a comment about the material, you can let me know. All right. Yeah, I'm gonna get through more of this material. Looks like things have slowed down here finally. Like Dude0122's comment on Vaughn.live. It's really cool. It's probably me playing Jew's harp. Who's responding to there. Check that out. That was last time. If whatever you're looking at captures it. There's an archive on Twitch or YouTube of a lot of these things. Find Somatica in those places. Um, all right, so yeah, thinking about F equals ma. It's completely useless because no prediction whatsoever can be made from a definition. But to find out what happens when two balls push against each other or when a weight is hung on a spring is another matter altogether. Because the way the bodies behave is something completely outside any choice of definition. If we were to choose to say that an object left to itself keeps its position and does not move, then when we see something drifting, we could say that it must be due to a gorse. A gorse is a rate of change of position. Now, we have a wonderful new law. Everything stands still, except when a gorse is acting. It would be analogous to the above definition of force, and it would contain no information. So the real content in Newton's laws is this, that the force is supposed to have some independent properties, in addition to the law F equals ma, but the specific independent properties that the force has were not completely described by Newton or by anybody else. And therefore, the physical law F equals ma is an incomplete law. It implies that if we study the mass times the acceleration and call the product the force, if we study the characteristics of force as a program of interest, then we shall find that forces have some simplicity. The law is a good program for analyzing nature. It is a suggestion that the forces will be simple. So what Feynman's saying is that you couldn't make a theory of gravitation that F is equal to mass times acceleration and call it a complete theory of gravitation because it's equal to, well, the size of it anyway. I'll write it the simple way. Is M1 is the two masses times the gravitational constant over the radius, the distance between them squared. Point out that that's, well, no, I'll just leave it unmarked. Yeah, a distance. So together this makes a complete theory, a complete theory of FG in terms of these things, I guess. Mass and radius, but you can describe the movement of things in gravity in terms of mass. Interesting. Um, we want to describe more than gravity anyway. So the deal with forces is that if a force is not equal to zero, then there's something that's influencing that body. That assumption is entirely different from the case of the gorse. I think monitoring all these streams simultaneously for chat is What of overhead. And so the third law is the equal and opposite thing. Oh, it's not exactly true. F equals ma is not exactly true. If it were a definition, we should have to say that it is always true, but it is not. And yeah, Feynman's pointing out that science is not math and it's not philosophy. So a physical law is and a physical theory have their own status as like propositions about the world and what is true. What is an object? Well, just take a chair, for example, philosophers always say. The moment they say that, you know they do not know what they're talking about anymore. What is a chair? It's a certain thing over there. Certain? How certain? Its material composition isn't constant, and not all the matter of the chair is functional. Is actually definitive of the chair. Is any matter definitive of the chair? Is a reasonable question because um, the function of the chair appears to result from a bunch of relations between the matter that is currently chair-like, and it's not really the matter, but the relations between the matter that encodes the function. So I'm riffing and not reading this literally, but this is related to the problem of mereology and organisms, the whole part relationships and selfhood that um, somatics nerds might be interested in. I know I've maintained a long term interest in these problems. Sorites or heap paradoxes. The trick is the idealizations. A mathematical definition will be good for mathematics, in which all the logic can be followed out completely. But the physical world is complex, as we have indicated in a number of examples, such as those of the ocean waves and a glass of wine. When we try to isolate pieces of it, to talk about one mass, the wine and the glass, how can we know which is which when one dissolves in the other? The forces on a single thing already involve approximation. And if we have a system of discourse about the real world, then that system, at least for the present day, must involve approximations of some kind. The system is quite unlike the case of mathematics, in which everything can be defined, and then we do not know what we are talking about. In fact, the glory of mathematics is that we do not have to say what we are talking about. The glory is that the laws, the arguments, and the logic are independent of what it is. If we have any other set of objects that obey the same system of axioms as Euclid's geometry, then if we make new definitions and follow them out with correct logic, all the consequences will be correct. And it makes no difference what the subject was. That's math. In nature, however, when we draw a line or establish a line by using a light beam and a theodolite, as we do in surveying, are we measuring a line in the sense of Euclid? No, we are making an approximation. The crosshair has some width, but a geometrical line has no width. And so whether Euclidean geometry can be used for surveying or not is a physical question, not a mathematical question. This is very helpful, I think. There are a lot of people don't have this basic distinction clear, that there's like a large distance between the 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 logic of mathematics and physics. The logic. There's a difference between like yeah, I didn't even say that very well. It isn't really the logic. It's the subject matter itself. Mathematics isn't actually concerned with the world, the real world. It's the world of ideas, which therefore live in the real world in minds, in nervous systems. F equals ma definition, deduce everything mathematically, make mechanics a mathematical theory, when mechanics is a description of nature. By establishing suitable postulates, it is always possible to make a system of mathematics, just as Euclid did, but we cannot make a mathematics of the world because sooner or later we have to find out whether the axioms are valid for the objects of nature. Thus, we immediately get involved with these complicated and dirty objects of nature, but with approximations of ever-increasing inaccuracy. I think I put an extra word in there. So, yeah, as an example of a complicated thing, let's talk about friction, the drag on an airplane. What is the law for a force, for that force? Approximately constant times the square of the velocity. What's the status of such a law? Is it analogous to F equals ma? The answer is not at all, because this is just empirical. It's obtained roughly by testing the wind tunnel. You might say, well, F equals ma might be empirical too. That is not the reason that there is a difference. The difference is not that it is empirical, but that as we understand nature, this law is a result of an enormous complexity of events and is not fundamentally a simple thing. If we continue to study it more and more, measuring more and more accurately, the law will continue to become more complicated, not less. In other words, as we study this law of the drag on an airplane more and more closely, we find out that it is falser and falser. And the more deeply we study it and the more accurately we measure it, the more complicated the truth becomes. So, in that sense, we consider it not to result from a simple fundamental process which agrees with our original surmise. For example, if the velocity is extremely low, so low that an ordinary airplane is not flying, as when the airplane is dragged slowly through the air, then the law changes, and the drag friction depends more nearly linearly on the velocity. To take another example, the frictional drag on a ball or bubble or anything that's moving slowly through a viscous liquid like honey is proportional to the velocity. But for motion so fast that the fluid swirls around, honey does not, but water and air do, then the drag becomes more nearly proportional to the square of the velocity. And if the velocity continues to increase, then even this law will begin to fail. People who say, well, the coefficients change slightly, are dodging the issue. Second, there are other great complications. Can this force on the airplane be divided or analyzed as a force on the wings, a force on the front, and so on? Indeed, this can be done if we are concerned with the torques here and there, but then we have to get special laws for the force on the wings and so on. It is an amazing fact that the force on a wing depends upon the other wing. In other words, if we take the airplane apart and put just one wing in the air, then the force is not the same as if the rest of the plane was there. The reason, of course, is that some of the wind that hits the front goes around to the wings and changes the force on the wings. It seems a miracle that there could be such a simple, rough empirical law that can be used in the design of airplanes. But this law is not in the same class as the basic law of physics, and further study of it will only make it more and more complicated. So yeah, I feel like he's kind of repeating himself again. This is kind of like talking about reductionism. And if you have an object like a plane, then interpreting the F equals CV squared law for the drag on it, or the F equals CV law if it's, I guess, in the viscous medium, interpreting either of those laws in terms of um, the actual structure of the plane, thinking about the whole part relationships of the plane itself, it doesn't simplify the matter. It turns into a very complicated story. Whereas good fundamental laws like F equals ma can be applied to successful reductionisms, that the forces add up in a way that makes sense, that the force on a little part of something is a little force, the force on a large part adds up to a larger force, and so you can do the whole part relationships of complicated structures um, using F equals ma in a more useful way. So it's a more foundational law. So you can say something's foundational if you can build things on top of it. It's another way of that's the logic that I'm kind of stuck with here. And successful reductionisms are built on the idea that there is a whole that is made of parts and that interactions between those parts add up to be present in the whole. And then there are examples in nature where the whole part relationships do not add up in a simple way. And so, yeah, Feynman's saying how this drag law, this structure of an airplane doesn't allow the whole part relationships to add up in a simple way. So that's not a foundational law. It's a practical empirical law. So more about friction. There's drag on an airplane, moving through air or through honey, dry friction or sliding friction. Yeah, I think he was saying dry friction. So, or dry forces on that first slide. So when one body, solid body, slides on another, a force is needed to maintain motion. This is called a frictional force, and its origin is also very complicated. To a very good approximation, the frictional force is proportional to this normal force. Oh, I need to actually read this better. Was the sentence just before. So the law is that the force needed to overcome friction and to drag one object over another depends upon the normal force, the perpendicular to the surface between the two surfaces that are in contact. Normals meaning perpendicular here. So there's the law for friction. Mu is this constant, the coefficient of friction. And N is the normal force, the downward force. No, it's the upward force. Well, no, I guess for sliding contact, the convention is that normal force opposes gravity. So that's how it would go. So if gravity is pointed down, normal force would be pointed up. The block is moving in a direction to the right, and the force of friction is opposing that motion to the left. And there's a resultant force that is being drawn here. I don't know what Feynman's going to say about the resultant force. It doesn't say anything about R. It's labeled, but so you've got a block on a plane and gravity force of gravity is pulling down on it. This is this arrow's too long. That's all right though. So here's the normal force. And so Fn is equal to Fg cos theta is what Feynman's saying here. No, sine theta. All right, so can I understand that from this geometry? uh, so so if we continue this to here, and we continue this down, and we can see that this is this line is perpendicular to this line. Um, so we'll call this angle x. So the angle it would help if this was longer. It would look better. Uh, so this angle theta called this one phi. And so theta plus phi plus 90 is equal to 180. So phi um, is 90 minus theta. It's the complement angle. It adds up to it at this plus this is equal to 90 degrees. Yes, it's kind of obvious now. Um, so there's an x and a y component to FG. And we want Fn. So if this is the right triangle we're looking at here, then well, in this triangle, if that's phi, then this must be theta here. And if this is theta in that part, then this has to be the angle phi over here. So then this has to be the angle theta over here. Okay. So then doesn't this look like the cosine of this angle? After all that work, I'm still thinking that this is because this would be the hypotenuse. This would be the opposite side and the adjacent side. That's not right. The gravity should be the thing on the hypotenuse, and it's the sum of the two other components. So this isn't the right triangle that I drew. Okay. Check in. I definitely lost my feet leaning over on my left foot. Some of my other concerns are going well. How are things with you? Is this tedious, watching me confirm this basic thing? I should figure out how to draw straighter lines. It's weird that I can't do this. It's something to do with as soon as I say that. What? Oh, okay. All right. Getting this tool, but all right. And it stopped working again. So weird. Right. So I should draw this arrow. Right. All right. Vector analysis. If I did the last chapter better, this would be going better. So if I um, take the force from gravity and I decompose it into a perpendicular component to the plane and a parallel movement to the plane, then those are the two components of the effect of gravity. And if I can just draw my perpendicular square better. So that's the forward component from gravity from the incline. And then over here is the normal force. Well, the normal force is opposite to that. Okay, that's the sign of it. That's the right. The normal force is actually it's directed in the sense opposite to gravity. So I can't wait to see his actual diagrams of this because I'm clearly messing it up. But I'm just trying to solve what is this angle here and what is its relationship to um, the force of gravity. So what I noticed was that these things are parallel. Well, this little triangle in here might be helpful. So this is similar to this triangle here. Did I think that might be helpful? Hmm. If that is theta, then this sine theta is the forward component, and this cos theta. But that must be the complement angle. Hmm. I guess I'm stuck. Yeah, I should probably do the vector chapter better before I try to spell that out. That was an interesting, 15, 20 minutes of watching me struggle. How am I feeling it? Yeah. It was a little work. It was a little work that I accumulated there. Just struggling live on camera was a little bit of work. Oh, downward along the plane. And normal to the plane. Oh, okay. This is confirming what I was figuring out. I just didn't read this carefully enough. Oh, that's hilarious. So yeah, that is the the sine component is going forward. So this is FG sine theta, and this is FG cos theta. But that's not Fn. That's negative Fn. Yeah, actually. All right. I guess I've unconfused myself. Oh, you missed all the whiteboard stuff. Anyway. Oh, no, you didn't. You saw it. Okay. It's the same. That's an interesting derivation of mu. Yeah. The tables that list purported values of mu, the coefficient of friction, for steel on steel, copper on copper, and the like are all false, because they ignore the factors mentioned above, which really determine mu. The friction is never due to copper on copper, but to the impurities clinging to the copper. In experiments of the type described above, the friction is nearly independent of the velocity. Many people believe that the friction to be overcome to get something started, static friction, exceeds the force required to keep it sliding friction. But with dry metals, it is very hard to show any difference. The opinion probably arises from experiences where small bits of oil or lubricant are present, or blocks, for example, are supported by springs or other flexible supports so that they appear to bind. So the science is hard here. To show that mu is nearly independent of velocity requires some delicate experimentation. Because the apparent friction is much reduced if the lower surface vibrates very fast. When the experiment is done at very high speed, care must be taken that the objects do not vibrate relative to one another, since apparent decreases of the friction at high speed are often due to vibrations. At any rate, this friction law is another one of those semi-empirical laws that are not thoroughly understood. At the present time, in fact, it is impossible even to estimate the coefficient of friction between two substances. And coming back to the pure substance, the metals sliding over each other, If we try to get absolutely pure copper, if we clean and polish the surfaces, outgas the materials in a vacuum, and take every conceivable precaution, we still do not get mu. For if we tilt the apparatus even to a vertical position, the slider will not fall off. The two pieces of copper stick together. The coefficient mu, which is ordinarily less than unity for reasonably hard surfaces, becomes several times unity. The reason for this unexpected behavior is that when the atoms in contact are all of the same kind, there is no way for the atoms to know that they're in different pieces of copper. When there are other atoms in the oxides and greases more complicated thin surface, I didn't read this very well. When there are other atoms in the oxides and greases and more complicated thin surface layers of contaminants in between, the atoms know when they are not on the same part. When we consider that it is the forces between atoms that hold the copper together as a solid, it should become clear that it is impossible to get the right coefficient of friction for pure metals. This is it's a related idea to this whole part relationships and um, complexity and good reductions. Good reductions are true, and bad reductions end up losing the truth in order to follow the reduction. And so, if you're thinking about a chunk of copper as being an object, a chunk, then it's true in part because of the non-copperiness and non-chunkness of the outside of that object. It ends up making it real. And so that if it comes into other pieces of copper, it doesn't just fuse with them like it's some kind of liquid that can just amalgamate things together. So its discreteness as an object and its imperfections, they have a relationship. Those imperfections end up making all the atoms of the copper into a unified whole. And here, imperfections aren't a value judgment, they're lack of conformity to total regularity. And that's related to the idea of information. Because if something's completely uniform, then it's informationless. It's got very, very high compressibility. You can describe what's in the room very succinctly when there's nothing in the room. The same phenomena can be observed in a simple homemade experiment with a flat glass plate and a glass tumbler. If the tumbler is placed on the plate and pulled along with a loop of string, it slides fairly well, and one can feel the coefficient of friction. It is a little irregular, but it is a coefficient. Now wet the glass plate in the bottom of the tumbler and pull again, we find that it binds. And if we look closely, we shall find scratches, because the water is able to lift the grease and other contaminants off the surface, and then we really have a glass-on-glass contact. This contact is so good that it holds tight and resists separation, so much that the glass is torn apart. That is, it makes scratches. Molecular forces. When they get very close, the force is repulsive. And then when they get some sweet spot, the force is attractive until they're too far apart, and then they don't feel the attraction anymore. That's what this is saying. Characteristics of molecular forces. The ultimate origin of friction. It takes QM to understand them, but empirically, the force between atoms is illustrated in that plot. And so this is, I guess, the thing shown here, right? Because it's falling off as forces, some constant. So the force is inversely proportional to the seventh power of the radius between the two things. Um, that's for non-polar things interacting according to their um, basic dispersion forces. And so we need to learn more about QM to understand um, why the forces fall off that way. But when there are dipoles, there are large, stronger forces, like electrostatic repulsion. Friction molecular forces, you can demonstrate them, like when we were sliding the glass tumbler. Two very carefully grounded lap surfaces, which are accurately flat, like Johansen blocks that are used in machine shops. If one such block is slid over another very carefully, and the upper one is lifted, the other one will adhere and can also be lifted by the molecular forces, exemplifying the direct attraction between the atoms on one block for the atoms on the other block. Hmm. Gauge blocks. Super precision gauge blocks that could be rung together to make up different lengths. Nevertheless, these molecular forces of attraction are still not fundamental in the sense that gravitation is fundamental. They are due to the vastly complex interactions of all the electrons and nuclei in one molecule with all the electrons and nuclei in another. Any simple-looking formula we get represents the summation of complications, so we still have not got the fundamental phenomena. Since the molecular forces attract at large distances and repel at short distances, as shown in figure 12.2, that one, that's great, I can mouse over and show it again. We can make up solids in which all the atoms are held together by their attractions and held apart by the repulsion that sets in when they are too close together. And so you can call this period where there's an attractive force a bond between the two atoms. And in one phase of this curve, if you're in this very linear part here, then it works as a Hooke's law spring where the force is proportional to the distance between the two things. It's very linear. So especially in this phase here, it's very Hooke's law regime. So fundamental forces. Electrical force. Forces between electrical charges. Looks just like the gravity law, but with signs. This is something I never learned. In working with electrical forces between fundamental particles, many people prefer the combination q electron, the charge on the electron squared over 4 pi mu naught, because it's between two electrons and 4 pi mu naught. So it's just the thing that's going to vary with distance. Right. talking about the field concept. Say that the charge at point P produces a condition at distance r such that when charge Q2 is at r, it feels that force. You can think that the force on Q2 at r can be written as in two parts. Is Q2 multiplied by a quantity E, that's the field strength, that would be there whether Q2 is there or not. E is the condition produced by Q1, and F is the response of Q2 to E. So E is called an electric field, a vector. So you've got the whole expression for the force between two things expresses the field with the influence due to the second thing taken out. It's the only thing taken out is the presence of the second thing. So that when you multiply them together, the field times the second thing gives you the force again. So it's just dividing the analysis in two parts. You do this with gravitation. In analyzing forces by the use of fields, we need two kinds of laws pertaining to fields. The first is the response to the field, and that gives the equations of motion. For example, in a gravitational field, the gravitational force is equal to mass times the field. Well, wait. Oh, yeah, right, yeah. Or if there's also a charge, right. So, yeah, that's the easy part. And the second part is the field equations that actually describe the field. The most remarkable fact of all, which is true exactly, which can be easily understood, is that the total electric field produced by a number of sources is the vector sum. Is that called superposition? Yes. 12.6 and 12.10. And same with the gravitational field. The total field due to all the sources is the sum of the fields due to each source. So superposition is exactly right for electrical charges and electrical fields, apparently, but it isn't for gravity, which is one of the hints that gives rise to Einstein's theory. There's magnetic force 2. Can be analyzed in terms of a field. Starts describing the apparatus for detecting that. So you're shooting an electron beam through a horseshoe magnet. So if you don't have the horseshoe magnet and you don't have any voltage on between those two horizontal plates here, then the beam goes all the way to hit the screen. And then if you turn on the voltage, the electrons get attracted to the positive plate, so they deviate upwards and have a Z displacement from the center. So you have an initial upward deflection, and then when you put oh yeah, and if you change the charge on this, then it deflects the same amount below, right? So you can see the effect of the electric field. You put the horseshoe magnet there,